Warning: vanadium compounds are toxic. Nitric acid and sulfuric acid are corrosive, and nitrogen dioxide gas is toxic. Wear gloves when handling them and work in a well-ventilated area. Hi guys, here is MIH. I've said in the last video that I'm going to retry the contact process of making sulfuric acid using a new vanadium pentoxide catalyst. And in this video, I'll be trying to make ammonium metavanadate, the precursor for the catalyst. This mini project was a whole lot more complicated and interesting than I thought it would be, and although I didn't isolate anything useful in the end, I was absolutely fascinated by the cool colors I saw in the process and the theories behind them. So let's begin. My vanadium source are these vanadium metal crystals. Although being heavily oxidized, its distinctive branched appearance is still very gorgeous. If you look closely on the crystal, you can see areas covered by a rainbow layer of oxide, which was really cool to look at. I weigh out around 1.5 grams of the vanadium crystals. To get the vanadium in solution, I would have to dissolve it, and I tried two different ways to do that. First, I added around 10 ml of 7% hydrogen peroxide. Immediately, you can see the vanadium being shiny and the solution turning yellow. The oxide layer on the vanadium is mainly composed of vanadium dioxide or vanadium 4 oxide, and it is readily oxidized by hydrogen peroxide to give peroxido complexes, which is bright yellow in color. As the reaction progresses, you can clearly see the shiny state of the vanadium metal, which is also very beautiful. The vanadium metal is reacting with the hydrogen peroxide to perform a series of vanadium 5 peroxido complexes, mostly diperoxido and triperoxido ones. They have very complicated 3D structures, as vanadium 5 species tend to condense together and form large clusters of vanadium oxyanions, such as the divanadate, tetravanadate, and decavanadate shown here. These peroxido complexes are not very stable, especially when heated, so they partially decompose and release oxygen bubbles. After a while, the reaction mixture turned to a dark red, possibly due to the decomposition of the yellow diperoxido and triperoxido complexes to orange-red monoperoxido complexes by the loss of oxygen gas. The red color can also be due to vanadium pentoxide or polyvanadic acid colloids. At this point, I'd like to draw your attention on the fact that vanadium doesn't dissolve in either boiling hydrochloric acid or sulfuric acid, but readily dissolves in room temperature hydrogen peroxide. Surprisingly, there are actually a few transition metals that are attacked easily by dilute hydrogen peroxide at room temperature, the most famous example being tungsten. These metals are mainly early transition metals, and they tend to bear high oxidation states like +5 or +6, and form large anionic clusters, each made from up to 100 or so metal atoms. On one hand, the metals form acidic oxides, which explains their inertness towards common acids, since they can't easily form stable cations with lower oxidation states. On the other hand, hydrogen peroxide is a ligand and favors the formation of complex cross-linked metal clusters, which explains the metal's reactivity toward hydrogen peroxide. But these are my guesses and deductions, and they're not yet confirmed. Whew, that was some complicated but cool inorganic chemistry theories. Now let's dive back to our experiment. As the mixture was gently boiled on a hot plate, the reaction speeds up and releases a lot of oxygen bubbles. The remaining hydrogen peroxide also starts to decompose rapidly. At a point when the camera was off, the mixture suddenly turned to a dark green. I suppose this is because the hydrogen peroxide was depleted and the peracids fully decomposed to vanadium pentoxide, and somehow the remaining vanadium metal reduced the vanadium 5 to vanadium 4 or 3, which has a blue to green color. This is just my guess, I don't know for sure. But when I add more hydrogen peroxide to the mixture, the green color quickly clears up and the yellow color of the peroxide complexes return, so the green color is likely vanadium in lower oxidation states. Since I'm running out of time, I transferred everything to a larger conical flask and let the mixture sit for a week. Here we are a week later. Apparently, the mixture has turned to a dark green with a lot of solids still not dissolved. Looking closer, there appears to be both vanadium metal and vanadium oxides remaining. I then added hydrogen peroxide to try to take away the green color, but the changes were less obvious this time, and the mixture only became brown-yellow. Upon heating, all of the green stuff eventually dissolved, and the solution turns to the familiar orange-yellow color, but a lot of vanadium is still left over. I kind of expected this to happen, so I added more hydrogen peroxide, and the color of the solution steadily deepened, but lighten after all of the hydrogen peroxide is consumed again. I think this hydrogen peroxide dissolution is too slow, so I decanted off the solution and washed the leftover vanadium with a little bit of water. I then tried the second way of dissolving it, and that is with nitric acid. Immediately after I add a few mils of 70% nitric acid, the mixture released a lot of gas and the solution quickly turned to the beautiful blue color of vanadium, which is VO2+ ions. The yellow and the blue solutions create a very beautiful and vibrant contrast, and you can hardly believe that they both come from a single element. Of course, good ventilation precautions must be present, since the nitrogen dioxide produced from the reaction is toxic. After a while, the reaction becomes much faster and the blue color deepens quickly. Meanwhile, the solution I decanted off before, which is supposed to contain mainly vanadic acid, produced a lot of green precipitates. This really confused me, as the vanadium was definitely all in the +5 oxidation state, but it somehow turned to this green thing. We've seen this color before, and it indicates that lower oxidation states of vanadium, +4 or +3, are present. On the other side, the nitric acid mixture didn't release gas anymore, but a lot of black powder still remains. I decanted the upper vanadium nitrate solution off, and tried to add concentrated sulfuric acid to the black powder, which I suppose is +4 or +3 vanadium oxides, or even a mixture of the two. The mixture turned to a dark red color, which I guess was vanadium pentoxide or even pervanadium, which is VO2+ sulfate. I then added some sulfuric acid to the beaker with the green precipitate, and it turned yellow too. Upon stirring, it completely dissolved into a yellow solution. I was relieved upon seeing this, as I'm pretty certain that this color is pervanadium ions. I then did the same thing and added sulfuric acid to the larger beaker of vanadic acid we had before, and a brown-red precipitate of vanadium pentoxide formed and it dissolved, creating the same pale yellow solution. However, as I'm doing this, the solution in the small beaker somehow slowly changed color, and by the time I finished adding sulfuric acid, it turned yellow-green. A moment later it turned to an emerald color, and I was again very confused by this, as it meant that there was some unknown reducing agent in the mixture that keeps reducing vanadium 5 to vanadium 4 and 3. I tried to add more sulfuric acid, but that didn't do anything. Interestingly enough, this unknown reducing agent might be hydrogen peroxide itself. Hydrogen peroxide is normally an oxidizing agent because of its 2 oxygen atoms at oxidation state -1, but it can yield to even stronger oxidizing agents to produce oxygen. Although I still have doubt if vanadium 5 is strong enough to oxidize hydrogen peroxide, I would say this is still the most reasonable explanation so far. Another evidence is that no color change was observed in the vanadium nitrate solution, which contained no hydrogen peroxide. But long story short, I didn't realize this at the time, and I simply combined all 4 portions of solutions together, 2 from the hydrogen peroxide trial and 2 from the nitric acid trial. I'm left with a dark green, strongly acidic solution containing mainly vanadium 3 and vanadium 4, as well as remaining sulfuric acid, nitric acid, hydrogen peroxide, and maybe some vanadium peroxide complexes. I boiled the solution for a long time to fully decompose all peroxides and remove most of the nitric acid. After an hour of boiling, I checked the pH to be around 2. I then gradually added a sodium hydroxide solution to bring the pH up to around 8. The solution quickly turned to a turquoise color and then a brown color, and dark brown precipitate of vanadium 3 and 4 oxide began to precipitate. Vanadium can only be effectively oxidized to +5 in an alkaline condition, so we're adjusting the pH to alkaline to separate the oxides, oxidize them to +5, and acidify them again to make the final metavanadate product. I've filtered the vanadium mixture and added a few drops of hydrogen peroxide to the residue on the filter. It immediately turned to a vibrant orange-red color, which is the color of vanadium +5. I then dissolved the vanadium pentoxide off the filter using a sodium hydroxide solution to create a solution of sodium orthovanadate, which is colorless. This solution is supposed to be converted to ammonium metavanadate by adding ammonium chloride, maintaining the pH around 8, and cooling down the solution. But no crystal seems to be formed after freezing the solution, and I don't know why. I think I simply don't know enough vanadium chemistry to have a good idea of what is going on in every step, so I likely messed one of the steps up in the middle of the process, and it just doesn't work at the end. Also, even if I did get some crystals of metavanadate, I introduced way too much acid and base to the solution, creating large amounts of salt, which will vastly contaminate my product. But anyways, I still found some really cool color changes during the process. For example, this is a solution of vanadium sulfate, and I add some sodium hydroxide solution. Initially, the two solutions don't mix, and the upper blue-green layer consists of vanadium ions, while the lower yellow-orange layer consists of tetravalent vanadate. As I shake the beaker, the solutions react to produce a dense precipitate of vanadium 4 oxide hydroxide, with the pH being perfectly neutral. Vanadium 4 is amphoteric, meaning that it dissolves in both acids and bases to give vanadium ions and tetravalent vanadate ions respectively, and only precipitates as vanadium 4 oxide hydroxide when the pH is close to neutral. Another series of color changes occur with vanadium 5 as well. If the strongly acidic solution of pervanadium sulfate is basified with sodium hydroxide, the mixture turns from yellow to green and blue, and finally to a faint yellow. Orthovanadate and metavanadate are colorless, but other condensed vanadate ions have different colors, ranging from yellow to red. These vanadate ions have very complicated interconversions in different pH conditions. Hope you enjoyed the vibrant colors and the intensive knowledge of this video, and see you soon.